Well, hello again. I'm Mr. Hernandez. Welcome to Honors Physics Lesson 5.3, Centripetal Force. Today we're going to investigate centripetal force. It's going to be a very illuminating time to learn about circles and the force that things go around. Let's begin. Alright, so centripetal force and motion. Centripetal force actually means center falling. So whenever we're looking at centripetal force, we're looking at a force that is directed towards the center of the circle, which also means that the acceleration is going towards the center as well as we go around, even though the velocity, and I'm going to try to catch this ball, is going tangent to that circle. All right, so a couple things. First thing we need to do is talk about this thing called centrifugal force and why you should never use the F word. Get it? Because it has an F in it. This is a fictitious or pseudo force, and basically what it wants to talk about is when something is spinning in a circle, the reason why that it's going and wants to release or get sucked to the side, kind of how a centrifuge works, is because there's some kind of inertial force, and that is not the case. What's actually happening is this inertia wants this object to continue doing what it's doing and move it in a straight line. So the mass of the object kind of tries to go in that straight line. The centripetal force keeps that in check because the acceleration is going down, and that spins it around. So inertia is not a force, it's a property of matter. Therefore, centrifugal force is not a force in this class. So there, ha, booyah! All right, so why things do feel like you're kind of getting sucked to the side, kind of like how this gravitron works, is again because of inertia. So your mass wants to move you in a straight line, and whatever is preventing that, either the string or a car door, if you're going around a circle, or in this case the gravitron, it's the wall, keeps you from doing that. And that is the law of inertia, Newton's first law. I love when forces work the way that we're supposed to work. All right, so let's talk about centripetal force because that's the force we really care about, not this fictitious centrifugal force, which now you will never use because it's the F word, and F equals bad. Ooh. All right, so centripetal force. This is our mass times our acceleration. Since we're dealing with the acceleration going around this circle, it's mv squared divided by the radius. And remember, the acceleration will always point in the direction of the force, which is towards the center of the circle. The velocity will be tangent to it. All right, so let's say we have an object, and it's going to spin around 6 times in 11 seconds. We're going to do some quick calculations here as far as figuring out the period of the object. So, period of the object should be the amount of time per spin, so 11 divided by 6, and that'll give us 1.83 meters seconds per spin. What is that velocity? So in order to figure out velocity, we're going to take 2 pi, multiply that by our radius, which in this case it's 2.5. So if you spin a rope around and it's going in a circle, the length of the rope is the radius of the circle. So 2.5. You don't have to cut that in half. And then divide that by our now 1.83, and you should get a velocity of 8.58 meters per second. As far as centripetal acceleration goes, now we're going to take that velocity, so there's 8.58, square it, divide by our radius, which is 2.5, and that should give us our acceleration, which is 29.45. Now to figure out the mass on that object, there's a different color, our force centripetal should equal our mass times our acceleration centripetal. So force is 70 newtons. That should equal our mass times 29.45. And we should get around 2.38 kilograms. All right, now for the super hard one. We have this tire-shaped space station, and it's given us the radius of 150 meters. We want to experience the acceleration of gravity that we have on Earth. So our centripetal acceleration should equal 9.8 meters per second squared. So this 9.8 meters per second squared is our acceleration. That should equal our velocity squared divided by our radius, which is 150 meters. And that'll give us our velocity, which is 38.34, but it's not asking for a velocity, it's asking the period the space station should go around. So we're going to take that velocity, 38.34, and we're going to plug that into our velocity formula, which has period in it. So 2 pi, our radius, which is 150, divided by our period, and we should end up with a period that equals 24.6 seconds for every one spin. It's going pretty fast. All right. Thank you very much, and I will see you next time. Same great place, same physics channel. Na 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 physics.